give you a second to read. I'll pass out the other one I've got too, so you can look at it. This is moving up to a more formal written version. I wrote out the formal one. And notice one of the things at college, I wrote this more than college level, but also reading across the curriculum format, use 2-column proofs.
I think that'll be, yeah, I feel the same. I feel your disappointment there, Tracy.
You can use them to get here, but the key here, in a from a formal sense, from a purely geometric sense, with a reflection, what you're doing is you're proving that with the angle bisecting this length, that C, or I forget which one I did. Let me look here, so I used the one I did there. B. I took B and reflected over. I want to prove that B actually does go to C. I don't know that. Yes, intuitively, one example shows it does. But how do I know that works?
Every time.
Every time. That's where the proof comes in. That's where the argument comes in. I'm arguing all my cases at once in there. So in terms of transformation, because I'm doing it via mappings, I first have to show that the ray AB, which maps to the ray AX, that AX is on ray AC. So I use the angle bisector to get me that. Angles give you more control. Then once I have that X is on AC, I either pull it into C or stretch it out to C using the length parts. So there's typically 2 steps involved. One is get the corresponding rays to match up, and then get the lengths to match up. Because what I want to do is show, in essence, I'm still showing that triangle APB is congruent to APC. But I'm showing that via this reflection, this triangle maps to this triangle. Yes, I get these two automatically. But I got to prove that B really does end up at C, not just picture. Remember, pictures can lie.
But if it's on.
I have an onto relationship, but that doesn't mean that B will go on to C. I've got to prove that part. So this is where it's so much more, this is where it's more challenging.
Yeah, it takes it to a different level,
It's
doesn't it?
that, but it's a different way of thinking. We're so used to using side angle side congruency relationship, we eventually get those. But you don't have those in transformational geometry. Like, you just got your reflection principle. How do you do it purely in reflections? That's where we've got to rethink everything. Is how do reflections do the job until I can build up the other tools? And it's gonna, trust me, been through it, still working on it. It's a whole another way of thinking that you've got to adjust the components. And it's a little uncomfortable at first.
You know, it just occurred to me, Todd, that Dr. McGee gave us in his presentation from the release items from the PISA exam, a reflection question, a transformation question. And maybe I'll just give that to you. I don't know that you've had a chance to even look at that. Maybe I'll just give that to you to have a look at it. And if you want to make a few comments about that tomorrow at some point, that would be good. I feel bad because I feel like we're out of time, and I
get 30 seconds at least talk the hand up.
Okay, absolutely, but absolutely, go. Thank you. Yes.
Now, one of the other ones we were going to do is the sum of the interior angles of a triangle is 180.
Yeah.
Okay, there are lots of ways to do this, and I'm structurally, your mirror activities did it one way. I'm doing it a slightly different because it's easier to write the proof. Now, you would have seen the proof, then I would have had you talk a little bit, then I would have given you the hint, then a translation, then I would show the picture. But the translation, again, you've got the formal written version. I'm taking this one, translating it down to here via this vector. So A will end up at B. I've got to, I don't even care if B ends up B prime because I want this angle. These 3 angles, which look like 180, I want to match them up to this one to that one to that one via transformation ideas. But also now, at this point, you would have built up the parallel postulate, all your parallel line relationships. I'm showing you can bring those in. The order of the topics show up when Euclidean geometry is nearly the same as they'll show up in transformational. It's just the tools you use are different. So part of it here is these two angles will be congruent because of the translation. That's preserved. Well, as soon as these two are congruent, this being a transversal says these two are parallel to each other. Once these two are parallel to each other, then those are congruent because I've got alternate interior angles relative to that transversal. I can still use those pieces at the point this would have brought in because I would have built up all the parallel line pieces. So I'm trying to show here is, yes, eventually you start morphing in transformational ideas and Euclidean. But you got to keep track of how they fit.
Thank you so much, Todd. I realize I asked you to do an impossible job to give us a bit of review of transformational geometry. You covered a lot of ground, and I really appreciate it.
I'm just going to quick highlight the pieces and you'll be reading later. Here's an additional problem. Here's an application problem. Here's a second application problem. You can read them later.
Are these? Do we have these, Todd, or
I will.
Oh, we will. Okay.
I want to edit something else in it here.
Sure.
Then I talk a little bit about similarity. So those that want some similarity, what's the terminology? The thing I want to point out here is look at the notes that'll be with the slides at the bottom.
Okay.
The language here is not universal. That's what I wanted to get to here. Yeah, it gets more complicated because with similarity, you got to be able to match up angles, but you got to deal with the length changes. The dilations are not always. Dilations aren't always dilation.
No, I know. That's what kills me about the new vocabulary.
Dilation is also called homothency.
I like that.
And the reason I switched, and that's in the notes, I didn't put it in here, because yesterday, what was it, Dr. Geo or whatever, what was that one we were looking at in the middle grades? Apps?
Dr. LG, no.
Dr. Geo or something?
Yes.
There's one of the apps, and it's kind of GSP-like, but we couldn't test it first, you had to buy it for. No, that's another one, it was Dr. something. One of the apps the middle grades looked at yesterday. They used homothency instead of dilation, which is why I could, oops, better mention that word. So look at the notes when these come out, because that gives you some of the alternative vocabulary. So I just summarized the big ideas. Okay, now I'll be quiet. For now.
Thank you very much, Todd.